If you are also looking for professional certified structural engineering services or courses, then don't forget to check link in description of this video.
So guys, let's start from where we left in the previous video. In the previous video, we have modeled the underground water tank using SAP2000, and then we did its analysis and we saw its results of movements as well as day shear. Now in this video, we will be doing the detailing and design of that underground water tank. If you want to learn that how to model underground water tank and how to apply loading in it in SAP2000, so you can go and watch out the video whose link is given in the description below. Now let's come back to this video. So if we talk about design, so the very first thing that we need is the material properties. We have already defined this in SAP2000 that we will be using 4000 psi concrete compressive strength. Then steel strength we will be using 60,000 psi. And based on this 4000 psi, the elastic modulus of concrete is 360, 49 and 7 psi. Now for designing, what we need from SAP2000. See, if I talk about this video, so in this video, I will be showing you the design of just simply one 13-foot long wall. For the remaining walls and slab, the procedure will be totally same, and you need to just repeat the steps which I will show you in this for this 13-foot long wall. So let's start. So for any shell element or area element, be it wall or slab, we need this. There should be M11, movement along x-axis, along x-axis. So guys, we need these three things from SAP2000. M11, it is the movement along x-axis. See, this is your 13-foot long wall, and this is what the movement along this horizontal axis, x-axis, is your M11. And using this movement values, what we will do, we will find the horizontal reinforcement that is needed for the wall. Then using M22, we will find the vertical, because M22 is what? M22 is movement along y-axis. So using this, we will get the vertical reinforcement. Then F12, F12 is your in-plane shear force. We will be checking it. If this is greater than, if this is less than shear capacity, then we are good. But if it's greater than shear capacity, then we need to provide shear reinforcement as well. Okay, so these are the three results that we will be checking from SAP2000, and then we will proceed with the design. So let's go back to our SAP2000 model. We need to go to Analyze, click on Run Analysis. Now we need to go to Display, Show Forces and Stresses, then Shells. Now, as I mentioned in the previous video, we will be seeing our results on three load combinations. The very first load combination is test phase, when only the water is present inside the tank. There is no backfill, there is no surcharge load, there is no lateral load of soil. So first we will, on this case, we will check M11 value. So let's go and check. So on this case, test phase M11, the movement along horizontal axis, here you can see in the middle, in the unit earning kept fit. Okay, so in the middle we don't have any significant movement, it's coming near to zero. Then at the, and it's positive. Then at the corners, at the edges, what we have negative movement, -1. It means it needs this is negative moment. So you know this thing, when the moment is negative, so we place the bars in what? In tension zone. Okay, in tension zones so it means the bars will be placed at the top. Now it depends how the load is being applied. So what I will be telling you the simplest way through which you can avoid this confusion, but later on in this video. Okay, so here you can see this is negative movement. So seeing the negative movement, it's clear in our mind that we need to place the bars in tension zone. Okay, that is at the top. Now, and it's how much? It's around minus 1.2. Let us see on other load cases. We will be taking that load case which gives us maximum value. So let's see on maintenance. Now in maintenance phase, here you can see from the contour, in the middle again we have 0, near to 0, and at the edges we have positive movement, and its positive movement and its value is also around 1.54, 1.32, similar to that as we saw in that test phase, but that was negative, it's positive. Mean that was its positive movement, that was negative movement. Now let's see on operation phase. Now again in operation phase, there is no any significant movement, neither on the edges, neither in the middle. So one thing is clear, that either in compression for positive movement we also need, for positive movement, let me show, for positive movement we also need 1.2 force, 1.2 kip feet, and for negative movement we also need 1.2 kip feet. That's the movement that we need. And here you can see I have put 1.33. Now let me explain you something over here, quite important, regarding the placing the reinforcement. See, if this is your section, if you have a positive moment, so in this region there will be what? If you have a positive moment, so in this region there will be compression, and there will, sorry, in this region there will be, in top region there will be compression, and then in the bottom region there will be tension. That's why what do you do when there is a positive movement? You place the reinforcement in the bottom. Now when you have negative movement, so what do you mean by negative movement? When you have a negative movement, so it means you will be having tension at the, when you have negative movement, the hogging, your tension will be at the top, your compression will be at the bottom, and then you need the reinforcement in the top. Now in case of wall section, this is your, let's say this, let me draw your wall. Let's say this is your wall. Now usually for 10-inch, the walls that are 10-inch thicker, more than 10-inch thick, we use 2 reinforcement layers. Code recommends that to use 2 layers for the walls that are greater than 10-inch thick. Okay, those walls which have greater than 10 inches thickness, the code recommends to use 2 layers of reinforcement. However, we also use, even if we have 8-inch thick wall, as in our case, we will use the 2 reinforcement layers. Okay, because it will serve my purpose. So my one layer, if I talk about the positive, if I talk about the what you say, M11. So M11 is this. It will be running like that. I'm not good with drawing, but you can just try to understand what I'm trying to teach you over here. So if we see section, so it will be your, it will be like that. it will be like that, somewhat like that. Okay, now when the moment is being applied, let's say it's like that. If I talk, let me draw in a good way so that you can understand it better way. If it's like that, right now the moment is like that. In the middle we have the positive reinforcement, okay, and at the edges, on one case there is positive movement all along the beam, and the other case there is negative movement. So negative movement means what? Your reinforcement should be placed at the top. Okay, your reinforcement should be placed at the, means it should be placed in the tension zone. So if I talk about wall section, so it means you need reinforcement in top, but for another case you need reinforcement at the bottom. So that's why we go for the reinforcement in two layers. I hope I try to make a point over here. Let me again try to teach you over this thing. Let me rub this again. I think so this concept is clear to you. That is when we have compression at the top, when we have positive movement, so we have compression at the top and tension at the bottom, and when we have negative movement we have tension at the top and compression at the bottom. Now then if we have a negative movement, so negative movement means your bar should go at the top, and if we have positive movement, it means the bar should come at the bottom. So that's why, that's the logic behind providing reinforcement in two layers. It's good. Okay, I hope so. I try to make a point over here. So that's why what we will be doing, we will be using this moment and we will be providing the reinforcement in two layers. Okay, we will calculate the reinforcement in first layer using this moment value, and again using this moment value we will calculate the reinforcement for second layer in M11 direction, horizontal, for horizontal reinforcement in two layers. Okay, so I hope so you get it. Then M22 is what? M22 is your vertical. So go to test phase M22. Let's check its values. So here you can see again positive at the in the middle. Then as you go to edges, so it start in negative and it's around minus 3.2, minus 2.4. Minus 2.4 is the maximum that I'm seeing. So it's mean tension. At the edges, what you can see, the reinforcement is in tension. There's negative reinforcement. Then maintenance phase. So in maintenance phase here you can see again you have at the edges you have positive movement, not negative movement. You have positive movement. Okay, and in the middle you have negative movement. So the easiest solution to this is provide the reinforcement in two layers using the maximum value, that is 2.46. Same was the case with that 2.46. Then let's see and goes and see operation phase. Now in operation phase there is no significant movement. So 2.4 we will be using. 2.88, okay, we can take it. It's good, and we will be using this value to design our vertical reinforcement in two layers. Okay, using 2.88 for one layer, then using 2.88 keep fit for another layer. Then F12, basically go to F12 and see its results. So the maximum value that we are seeing is around how much? Let's on test phase we are getting the maximum value of around minus 0.84 kip. Okay, then in maintenance phase we are getting around 700. Okay, okay, so 0.88 would be around, that would be fine. 0.98 kips we have taken. Okay, it's fine. 0.98. I think so. That's the test phase value. Yeah, here in this region, that's what we have taken in our design sheet. So now we have got the results from SAP 2000. Now what I will be doing, first I will be making sure that my shear capacity of my area element is okay. So first I calculated the distance D. That is simply how do we calculate it? Your depth of your thickness of your wall minus the concrete cover, and then minus the half of bar dia. Here you can see R15 is what? It's our thickness. Then minus 3-inch cover, and then minus half bar dia. Then how I have calculated this 5 EC. So let me take you to reinforcement references. As here you can see, basically this code clause has been taken from ACI 350, which states that 11.6, if in plane, that is F12, is less than equal to 0.5 phi alpha c lambda radical FC, then we are allowed to take, then we do not need to provide any shear reinforcement. That's simple. You can read it. You can go and read the code. Okay. Simply, either you can use this formula, or if you can go and use another code clause 38. This was as per ACI 350, or I can show you another code clause that was ACI 3811, which states that if you basically to check the shear capacity, it's like that. Let me show you. Let me show you that code clause. I think so. It should be over here. I place it over here, but if it's not there, let me go and find it for you. So guys, as per ACI 3811, to check the shear capacity of a member subjected to shear, you can use this formula. So if your F12 is less than this, you don't need to provide shear reinforcement. Simple as that. Then now I will show you how I have done the calculation for the reinforcement for Flexural M11. That is our horizontal reinforcement. So I have calculated the RU, that's equals to MU over BD square. You can find this formula in any of the reference book of structural design. RU is equal to MU over BD square, where MU is your moment that you are getting from SAP 2000. B is the width of the section. That is, in our case, it's 12. We will be taking for shear elements, we take 12 inches. Okay. D is the depth of your thickness of the wall. So you will calculate this. You will use D value of, that is D, you will be using this one value of D. Okay. That is minus cover and minus concrete flexure. Based on this value, you will calculate RU. Then using RU, you will calculate the reinforcement ratio that is needed for us using this one formula. The things are pretty much simple over here. No need for explanation, I think so. And then you get this reinforcement ratio. Now using this reinforcement ratio, multiplying with the section dimension, you get this area of steel that is required to cater our movement. But ACI code give us that we should if our reinforcement ratio is below threshold, then we need to use minimum reinforcement ratio. So let me show you the references from where you can make sure that your thicknesses, you should give minimum reinforcement. Let me show you the code clause for minimum reinforcement. You can also find the relevant code clause in ACI 350 and also in ACI 318. I can show you both. So here you can see, let me first show you in ACI 350. So that's basically in ACI 318. You can find it in ACI 31811 that a minimum area, this minimum area should be given. If you multiply 3 with radical FC over Fy, you will get around 0.003 BD, which formula I have used in the Excel sheet. Okay, so using this formula, you can get the minimum area of steel. If your area is coming less than that, then you should use that minimum area of steel, which we will be using. Then this this is from ACI 350, that minimum ratio of vertical reinforcement area to gross area, minimum ratio of vertical reinforcement area to gross concrete area shall be 0.003. This is for vertical reinforcement, but same is the case for horizontal reinforcement area. Minimum ratio of horizontal reinforcement area to gross concrete area shall be based on the length of between movement joints and shall conform to this table. Now in our case, let me show you that table. This one is the table. Now in our case, we can take this value 0.003 because there is no basically our wall is less than 20 feet, so we can take this 0.003. So same is the case, either you take ACI 318 code close, or you can check you can take the ACI 350. They are just reference. Okay, so in our case, we will be, minimum will be governing. Then we select the bar that we are going to use. You can select any of the bar. I am selecting number 4. Now based on this bar and based on the area required that we are going to take, that is 0.288, our spacing is coming that we have to provide 8.16 inches. The horizontal reinforcement should be at what you say spacing of 8.167. How you calculate a spacing? Simply 12 into area of bar upon area of steel. You will get the spacing. Now how much spacing I am providing? I am providing 10 inches spacing. Okay, so if I provide 10 inches spacing, so my provided area will be 0.35. That's not desirable, so I reduce the spacing. I make it 8 inches. So using 8 inches spacing, what I did, what happened, that I got the the 0.294 inches square as my area provided. Then I have also make sure that my section has enough capacity. So the moment capacity for our section comes out to be 5.667 with our provided reinforcement and material properties. The section strength that our section has, it's 5.667. Okay. Now the reinforcement that I have calculated over here, in the very first layer you will provide this reinforcement. Again in the second layer you will provide the same reinforcement in this same layer. So even then the section capacity would increase. This is for such single layer that we have calculated over here. But as I mentioned, it is good to provide in 2 layers, no matter if you have 8 inches thick wall. Okay. So this comes out to be moment capacity. How did I calculate this? First I calculate the value of A using this formula. Then for moment capacity I use, it's simple formula, it's ASFY D minus A upon 2. That's what I have written. I have not mentioned over here, but that's how I calculate the moment capacity. And since it comes out to be less than our required moment, so it's okay. Then we need to make sure our section is tension control, for which I require C value. First I calculated the C value using A value. It's simple. You can find this thing in any design related textbook. Then for tension control, we know this thing that our strain should be greater than 0.005. So guys, since our value of strain was coming out to be greater than 0.005, so it means our section is tension control and we are good to go. Now guys, before moving towards a Flexural M22, I will show you how to detail this horizontal reinforcement which is also known as distribution reinforcement. Guys, you are allowed to go for bar lesser than number 4 in horizontal reinforcement. That is distribution bar, you can go less than number 4. You can go with number 3 bar. But today we will not be doing that. We will be staying with the number 4, and we will be keeping its spacing 8 inches. Guys, see, as far as this video is concerned, we are not doing an economical design. We are just designing it. Okay, if it happens when you have to design it economically, then we can more by looking at the movements across the whole section of the walls, complete wall, we can play with the reinforcement in a quite smart way, and we can reduce our reinforcement amount. But that's not our goal of today's video. In today's video, I have to show you that how you can get the reinforcement from the movements from SAP2000. So as I mentioned over here, it's number 4 bar. Using number 4 bar at spacing 8 inches. This is how you're gonna detail number 4, 8 inches. Both ways, 2 plus 2 layers will be moved. Okay, this here you can see, this is your distribution bar. This is number 4, 8 inches. That will run throughout the length of the wall. Okay, so sorry, height of the wall, throughout the height of the wall. Okay, it will run throughout the length and along the height. Number 4, 8 inches center to center. Now this was for horizontal reinforcement. Now we will be talking about this vertical reinforcement, as here you are seeing. Okay, so let's get back to our Excel sheet. And similarly for M22, that is movement along y-axis, our vertical reinforcement. So in this case also, it's number 4 bar we are selecting, and then spacing required is coming out to be, because we are taking this one area, we do not have to take this one area. Instead of that, we have to take that we are actually controlling, that is this one. Let me see over here. I think that there's some problem. Let me see. Okay, the minimum area is coming out to be how much? It was coming out to be, in this case, it was coming out to be okay, wall thickness. Basically, we have to take wall thickness into account. No? Here there is a mistake in the formula. Let me correct it. It will be not this one, R69. Instead of that, it will be this D. Okay, so and here we have to take our controlling. The procedure is same, guys, I was explained you above. So again, it requires 8 inches spacing. We are providing how much? We are providing 8 inches. So 8.1 inches is required, we are providing 8 inches. 8.1 inches is required, we are providing 8 inches. So again, let's go back to our drawing. As here you can see, number 4, 8 inches center to center. These vertical reinforcement. Now if I talk about slab, so let's go back to our SAP model. Display, show forces and stresses. Let's see the moment of display, show force. Display, show forces, stresses, shells. M11, and we will be seeing its result on our 3 load combinations. Apply. So in test phase, let me keep fit. We are getting positive movement at the center around 2 kip fit, and at the edges -5. Okay, -1, -5. The maximum movement is coming out to be -5 in M11 direction. Then in maintenance phase, let us see. So again, there is no significant movement in the center in maintenance phase because there will be no water. No? That's why. So in maintenance phase, we won't find any much forces in the slab. Now operation phase, let us see operation phase. Again in operation phase we are getting the around -5 -6 movement at the edges, and at the positive movement around 2 kip fit, 2.5 kip fit in the center. So what we'll be doing, we will be designing our we will be taking the movement along M11 as 6 kip fit. Okay, so I will use the same sheet, okay, for that I have used for the wall. Just I will be changing its value over here because the procedure is almost similar. So 6 kip feet M11. Okay, now if this M11 is 6 kip feet, so let us see, RU is coming out to be this one, and then area of steel is coming out to be 0.312, and our minimum is 0.288. So 0.312 will be controlling one. So that's why it requires spacing to be, it requires if we choose number 4 bar, so it requires spacing requires around 7.5 inches. So what we will be doing, we will be providing number 6, we will be providing spacing of 6 inches. So in this way our provided area will be greater than required area. So this will be our for flexure reinforcement, for reinforcement along M11 direction, and it will be provided again in 2 layers. Now let me show you in our drawing. Here you can see let's say if this is your let's say so here you can see we have provided number 4 6 inches, that is number 4 6 inches in 2 layers. Same for the, let us go and check the M22 test phase, -6, and operation phase, it's again, it's coming out to be around 7. Okay, around 7. So if we use 7 over here, M22 as 7, so we need 0.368 inches square area is required. Number 4, so the spacing required is 6.395 inches, and we are providing 6 inches. So again we are good to go. That's why again I have provided over here number 4, as here you can see number 4 at 6 inches center to center in 2 layers. So that's how you do the design and detailing of underground water tank for wall and slab. So that's all for today. We'll meet you in the next video. Till then, goodbye.